The prevailing scientific consensus regards the Big Bang theory as the primary explanation for the universe's origins. According to this theory, the universe began as a singularity, an infinitely dense and hot point, around 13.8 billion years ago. This singularity rapidly expanded, leading to the formation of everything we observe today, including stars, planets, and life forms like us. While the name Big Bang may seem whimsical for such a monumental event, it vividly captures the concept of a colossal explosion from which the universe emerged. The process unfolded over billions of years, with matter spreading out and cooling down, eventually forming galaxies, stars, and planetary systems. Despite its widespread acceptance, the Big Bang theory has faced challenges over the years as new data and observations have emerged. When NASA launched the James Webb Space Telescope, it was hoped that its unprecedented capabilities would provide further evidence supporting the Big Bang theory. However, after just 1 year in space, the telescope began capturing images that challenged existing scientific understanding. These images revealed galaxies so ancient that they could potentially reshape our understanding of the universe's beginnings. The story of the James Webb Telescope's groundbreaking discoveries begins with astronomer Rohan Naidu's remarkable findings. While analyzing early telescope images in July 2022, Naidu stumbled upon a galaxy unlike any seen before, which he and his colleagues dubbed as Glass Z13. This galaxy dated back just 300 million years after the Big Bang, making it one of the oldest galaxies ever observed. The discovery of Glass Z13 sent shockwaves through the scientific community, exceeding even the most optimistic expectations for the James Webb Telescope's capabilities. Positioned millions of kilometers from Earth's interference, the James Webb Telescope was designed to explore cosmic dawn, the era just after the Big Bang when the first stars and galaxies began to form. Equipped with a giant segmented mirror and highly sensitive instruments, the telescope aimed to uncover details of this scarcely explored period in cosmic history. However, the telescope's initial findings defied expectations. Instead of detecting faint, distant galaxies as anticipated, astronomers discovered numerous galaxies with unexpected characteristics, including age, size, and brightness. In response to these unexpected discoveries, scientists intensified their efforts to understand the implications of the James Webb Telescope's findings. They embarked on further observations and analyses, seeking to unravel the mysteries of the early universe and refine our understanding of its origins. As researchers delve deeper into the cosmos with the James Webb Telescope, they continue to uncover new insights and unexpected phenomena. Each discovery brings us closer to unlocking the secrets of the universe and understanding our place within it. The discoveries made by the James Webb Space Telescope have raised profound questions about the nature of the universe and our understanding of its origins. While it's possible that these discoveries could be reconciled with standard cosmological models through further analysis, they also hint at the possibility that the universe is far more complex and mysterious than previously imagined. The early revelations from JWST have the potential to rewrite the opening chapters of cosmic history, not only concerning distant epochs and galaxies, but also having implications for our own existence here in the Milky Way galaxy. Mark Makorian, a senior advisor for science and exploration at the European Space Agency, aptly captures the essence of scientific exploration, building machines not to confirm existing paradigms but to challenge them. The journey toward the James Webb Telescope's groundbreaking discoveries traces back to the Space Telescope Science Institute in 1985. At that time, the Hubble Space Telescope was still years away from launch, but visionary leaders like Riccardo Giacconi saw the need to plan for the future, leading to the conception of the Next Generation Space Telescope, later renamed JWST. The NGST was envisioned to overcome the limitations of Hubble by observing in the infrared spectrum. This capability would allow it to peer deeper into the universe, capturing light from galaxies that had been stretched into the infrared due to the expansion of the universe. The decision to focus on observing early galaxies became the primary science goal for JWST, highlighting the telescope's potential to revolutionize our understanding of cosmic dawn. The need for a telescope like JWST was underscored by the groundbreaking observations of the Hubble Deep Field in 1995. Despite initial skepticism, the extended observation revealed thousands of galaxies stretching back billions of years into the history of the universe. This discovery demonstrated the richness and complexity of the early universe, setting the stage for JWST's future observations. After more than 2 decades of development at a cost of approximately $10 billion, JWST finally launched on Christmas Day 2021. Its arrival at its deep space destination marked the beginning of a new era in astronomical exploration. In July 2022, JWST commenced its first year of science observations, known as Cycle 1, with high-impact programs aimed at uncovering the mysteries of the early universe. Two of these programs, the Cosmic Evolution Early Release Science Survey and the Gravitational Lensing Amplified Survey from Space, were dedicated to searching for galaxies in the early universe. Despite initial expectations, JWST observations immediately revealed extremely distant galaxies, challenging previous assumptions about the timeline of galaxy formation. These discoveries have ignited excitement and speculation among astronomers, hinting at the possibility of even more profound revelations to come. The James Webb Space Telescope stands as a testament to human curiosity and ingenuity, poised to unravel the mysteries of the cosmos and reshape our understanding of the universe's origins. The discoveries made by the James Webb Space Telescope have ignited a profound reevaluation of our understanding of the early universe. A significant aspect of these revelations revolves around the unexpected brightness and size of galaxies observed at extreme distances, challenging conventional cosmological models. Thanks to a 29 upgrade that enhanced the telescope's infrared capabilities, JWST has been able to push the boundaries of observation, allowing scientists to peer deeper into space and further back in time than ever before. A redshift of 11, corresponding to a cosmic age of about 410 million years after the Big Bang, was previously considered a pivotal point when galaxy formation was thought to commence. However, JWST's early observations, particularly those from the Gravitational Lensing Amplified Survey from Space, revealed galaxies like Glass Z13 with a redshift of 13, indicating an age of approximately 300 million years closer to the Big Bang. These galaxies were unexpectedly bright and massive, challenging existing theories about the timeline and mechanisms of galaxy formation. The rapid emergence of galaxies with estimated redshifts as high as 20, just 180 million years after the Big Bang, defies the expectations set by the standard cosmological model known as lambda cold dark matter LCDM. LCDM incorporates scientists' best estimates for the properties of dark energy and dark matter, which collectively govern the emergence of large-scale cosmic structures. According to LCDM, the formation of large galaxies should have taken much longer, as it requires the slow action of matter over billions of years. To understand the implications of these discoveries, it's essential to consider the early stages of the universe's evolution. In the first second after the Big Bang, the universe was a hot, dense soup of primordial particles. Over the next few minutes, as the cosmos expanded and cooled, the first light elements began to form. Approximately 100 million years after the Big Bang, conditions became suitable for the emergence of the first stars. These early stars, devoid of the heavier elements present in modern-day stars, were larger and brighter, coalescing into protogalaxies that eventually formed larger galaxies over billions of years. JWST observations challenge this narrative by revealing galaxies that appear larger and more mature than expected at such early cosmic epochs. The absence of numerous smaller protogalactic fragments suggests that the process of galaxy formation may have been more rapid and complex than previously thought. While some galaxies may appear larger due to dust obscuration, follow-up observations with instruments like the Atacama Large Millimeter Array in Chile have confirmed the absence of significant dust in some cases, indicating that these galaxies are indeed exceptionally bright and massive. These findings have profound implications for our understanding of the universe's early history and the fundamental principles of cosmology. They suggest that the standard cosmological model may require revision to account for the unexpected observations made by JWST. Further exploration and analysis will be crucial in unraveling the mysteries of the early universe and redefining our understanding of cosmic evolution. Bo and Killian pointed out that the discoveries made by JWST could have significant implications for our understanding of dark matter and gravity. He mentioned a controversial idea called modified Newtonian dynamics, which suggests that the effects attributed to dark matter could instead be explained by large-scale fluctuations in gravity. According to Bo and Killian, JWST observations could potentially support such a theory. Matti Maghrabi, a proponent of modified Newtonian dynamics, highlighted that many of its predictions have been validated, suggesting that it may offer a viable alternative to the existence of dark matter. However, not all scientists are convinced of MIN's validity. Kartik Sheth, an astrophysicist at the Rochester Institute of Technology, expressed skepticism, stating that man has yet to provide satisfactory answers in many tests. Another possible explanation for the unexpected brightness of early galaxies is the lack of dust. Galaxies in the early universe may have had little to no dust, making them appear brighter than expected. This could complicate efforts to accurately calculate the galaxy's true masses and may also explain why ALMA had difficulty spotting glass Z13. Andrea Ferrara proposed that perhaps the dust in early galaxies was expelled during the initial phases of galaxy formation, leading to their brightness. Rebecca Mason and her colleagues suggest that JWST may be observing only the brightest young galaxies in the early universe, which would be easier to detect. Mark Spahn, a theoretical astrophysicist, proposed that high-mass star formation was very efficient in the early universe due to higher gas pressures and temperatures. He speculated that magnetic fields might have emerged earlier than previously thought, driving material to initiate star formation. The rapid dissemination of scientific papers following JWST's initial observations reflects the urgency and excitement surrounding the telescope. As discoveries, instead of the traditional peer review process, astronomers opted to publish their findings on Arxiv, a website where scientific papers can be uploaded and accessed by the scientific community without delay. The rapid dissemination of scientific findings following JWST's initial observations led to a new form of peer review unfolding in near real time on social media platforms like Twitter. Dubbed Science by Tweets, this phenomenon allowed for intense and surprising discussions among scientists. While this approach facilitated quick publicization and discussion of findings, some expressed concerns about rushing the process. Klaus Panepidden, JWST project scientist at the Space Telescope Science Institute, highlighted the importance of traditional peer-reviewed papers as the gold standard in scientific validation. Early calibration issues with JWST, for instance, may have affected some results, prompting calls for caution. Nathan Adams of the University of Manchester and his colleagues found dramatic changes in redshift measurements for some galaxies, underlining the need for careful analysis. Despite potential calibration issues, astronomers remain optimistic about the significance of JWST discoveries. While it's unlikely that all findings will be invalidated, the sheer number of high redshift galaxies detected suggests that the early universe may be different from what was initially predicted. In response to these discoveries, astronomers are racing to conduct follow-up observations with JWST to confirm and scrutinize high redshift galaxy candidates. Nancy Levinson, interim director at the Space Telescope Science Institute, revealed that numerous proposals are under review, seeking additional JWST observing time to study these galaxies further. Projects like Cosmos Webb, led by J.N. Karteltep, aim to significantly increase the known population of early galaxies by observing a wider swath of the sky for extended periods. Additionally, astronomers are exploring ways to detect evidence of the first protogalaxies, possibly using the deaths of supersized first stars and luminous supernova. The excitement surrounding JWST discoveries marks the beginning of a new era in astronomy, characterized by rapid communication and collaboration among scientists. Despite uncertainties, the prospect of reevaluating our understanding of the early universe has invigorated researchers. As Rohan Naidu aptly put it, confirming even a handful of these high redshift galaxies would be quite amazing, demonstrating that we are not being misled in our quest to unlock the secrets of the cosmos.